Okay, everybody. I am David Malone. I'm talking about some work that I've been doing with Hazel Murray. Hazel is going to handle the second half of this talk, and I'm doing the introduction here. And we're talking about a multi-armed bandit approach to password guessing, and I'm going to have to explain what multi-armed bandits are. And I guess most of us know what password guessing is. So what's the plan here? Well, I want to motivate what we're doing. This is going to be hopefully an interesting way of guessing passwords. And so where are we coming from? The technique that we're going to use to inform how we're going to guess these passwords is going to draw on the multi-armed bandit problem. So I'm going to tell you about that. And then I'm going to have to explain how we're going to use that to guess passwords. There's a little technical bit in the middle here where I'm going to tell you a little bit about how we're doing the multi-armed bandit stuff. This uses something called maximum likelihood estimation. So I'll give you a quick explanation of what we're doing there. And then maybe the more interesting bit is how we're using this to inform our guessing choices. So I'll tell you about that. And then once we get to there, I'm going to switch out, let Hazel take over, and she's going to tell us about the results that we've seen, which is really the interesting part here. So what's our motivation? I guess lots of us have seen that if you look at a password data set from Facebook, the word Facebook tends to crop up in it. And you see that people, when they sign up for a website, they're often thinking about the website, and they're the kind of words that come into their head. So you see the word Facebook associated with Facebook, LinkedIn with LinkedIn, but you also see words like job search, which is something that's on people's mind when they're in LinkedIn or when they're signing up for LinkedIn. So between similar types of websites, you might expect similar types of passwords to crop up. Another thing that you see often is that the passwords are influenced, of course, by the demographics of the people who are choosing them. So we have a password data set which came from Ireland, and you see words like Dublin cropping up on it. You see words, you see the names of sports teams that Irish people follow. And it's not just the things that people are interested in that you see cropping up in these data sets. You also see things like the language people speak having an effect on the passwords they choose, which is perhaps not a big surprise. So what's our goal here? Given that we see these sort of clusters of properties in password data sets, can we somehow use that to guess in a better way? So this is an interesting question. Could you recognize this automatically? And could an attacker maybe use this to guess in a better way? Because attackers, we know, will have lists of passwords that have been previously leaked. And if they can match a list of passwords to a data set they're trying to guess, perhaps they can guess more efficiently. So how are we going to do this? This is where this multi-armed bandit thing comes in. So what is a multi-armed bandit? Well, you can see a picture now of one-armed bandits. These are gambling machines that you'd see in a casino in various places. And the idea is they have an arm on the side of them. You pull the arm and you win with some chance. And the interesting thing about these machines is sometimes the machines are set up differently. So different machines pay out different amounts with different probabilities. And if you have a row of machines that you could possibly play, this gives you a sort of dilemma because you would like to play the best possible machine to win as much as possible. But at the same time, you don't know which is the best possible machine. And your way to find out involves playing each of the machines. But of course, that wastes money. And so the multi-armed bandit problem is how do you try and optimize these two things at the same time, playing the best machine and learning which is the best machine. And they're both using up your money simultaneously. So how does this relate to password cracking? Well, a password attacker, either doing cracking or doing online guessing, is using guesses. This is like their currency that they're spending to try and get some good result. They also have different dictionaries that they can draw on. So maybe they have dictionaries in different languages. Maybe they have these password data sets that we all look at to see how people are choosing their passwords. They may even have more personalized information, maybe names, addresses, blog posts perhaps that people have made, and maybe they're using all of these to inform their guesses. And what are they trying to do? Well, the way we've drawn it here, we have a set of hashes, and they're trying to crack these hashes and see if they can find the passwords within their dictionaries that match the hashes that they're trying to crack. So how are we going to take a multi-armed bandit approach to this? Well, On the one side here, we have a list of dictionaries that we can use for getting guesses for a password from. And on the other side, we have our hashes. And what do? Well, we have a look at our dictionary and we make a guess. So suppose we make 1, 2, 3, 4, 5, 6 as a guess, which we know is a very common password in lots of data sets. In doing that, we learn something about the people in the data set. So maybe we go through, we try cracking all of those hashes, and we find that 8 of the 200 users in our password set used 1, 2, 3, 4, 5, 6. Well, that tells us something about the demographics of the people using the password set. And we can go and have a look at the demographics of the dictionaries we've collected. Perhaps one of them, only 1 of 90 people used it, another one, 8 of 200 used it, and another one, 40 of 150 used it. And we could have a look and see which one matches best. So in this case, we've set it up nicely. So this purple dictionary in the middle has a really good match because 8 of 200 matches 8 of 200. But in general, what we're trying to do is we're going to weight the dictionaries. We're going to give probabilities to see which dictionary seems to match the password set best. Then we could make another guess. We get some more information. And each time we make a new guess, we get more information. We can try and reweight our dictionaries to see which one is best. And we go back and forth between guessing, learning some proportions of the demographics of the password set, and using that to see which dictionaries match best. So there are 2 things going on here. One is trying to pick out these proportions, and the other one is making informed guesses. So let me tell you how we're doing the 2 of these things. The first one, we're using this maximum likelihood technique. Essentially, this is a sort of standard probabilistic statistical method where what we are doing is we are pretending that the dictionaries have been sampled with particular probabilities to give the password set that we're trying to guess. And maximum likelihood gives us a way to estimate these weights Q for each dictionary. So we have a weight Q1 for dictionary 1, Q2 for dictionary 2, and so on. And maximum likelihood gives us a way to do this. It gives us an optimization problem, which usually we can't solve in a nice way. And instead, what you need is some kind of numerical method that finds the best likelihoods. And we do this, in this case, using a gradient descent, which is a completely standard way of handling this. So essentially what the maximum likelihood bit here is doing is it's giving us an estimate of the weights for these dictionaries, which one looks like it's best. On the other hand, how we're guessing is perhaps a more interesting question. So when we come to choose a new guess from a dictionary, how do we do that? And we have a couple of options. So one way is we could just randomly choose a dictionary, take the next best password out of that dictionary and guess it and see how we do. And this would be analogous to the multi-armed bandit problem of just going and trying each machine randomly, and you learn lots about the machines, but maybe you're not exploiting the best dictionary. Another option would be to have a look at the weights for the dictionary and see which one has the heaviest weight and use that dictionary all the time. And this one is exploiting the information we have the most, but it's not really kind of doing a balance between the 2. So we have a third option, which we call the Q method, because it involves calculating some probabilities that we called Q. And let me explain just how we do this. So let's take a simple example. We have 2 dictionaries here, dictionary 1. You can see the 8 passwords in dictionary 1 there, and you can see the 8 passwords in dictionary 2. And how are we going to choose which password to use next? Well, what we do is we have a look at the Q values we've calculated. So there have been some previous guesses. We've decided it looks like dictionary 1 is about 30% relevant, dictionary 2 is about 70% relevant. And then we have a look at the password hello, maybe, and we calculate a probability here for hello being good. We see it occurs once in the first dictionary. That's once out of 8. So we give it a weight of an 8th. And then in the second dictionary, we see it occurs twice out of 8. So that's 2 out of 8. And we combine that using the Qs to give a probability of hello being the password. And this is interesting because even though by occurs more often in this in these 2 data sets overall, it occurs 3 times in the first one and once in the second, because the first dictionary has a lower weight, we would actually weight this password with a lower weight in the end, and so we would guess hello as the most likely next password. So let me hand over now to Hazel, who's going to explain the results that we've got using this method.
Hi, so I'm going to talk about the results of our multi-arm bandit model. So I'm hoping to show you the multi-arm bandit model can do three things. So firstly, it can identify which source a set of leaked passwords comes from. Secondly, it can identify the nationality of users in a leaked password dataset. And finally, it can improve password guessing. So I'll look at the first one first. So that's identifying the source. So in order to investigate this, what we did is we took three password leaks. So we took, there was 7,300 passwords from a Hotmail leak, 100,000 passwords from FlirtLife, 15 million passwords from Webhost, and then computerbits.ie is an Irish site, and that had 1,795 passwords leaked from it. So what we did is we took 1,000 passwords from the FlirtLife dataset at random, 1,000 users' passwords, that is, and we made a new password dataset. So when we apply the multi-arm bandit, we expect it to be able to say that the passwords in our password set that we've created match best with the FlirtLife passwords. So what I've plotted here is the number of guesses on the x-axis, and on the y-axis, I'm plotting what the weightings it estimates. So what we'd expect is that FlirtLife would be approximately weighted as 1 because we know all the passwords came from FlirtLife, and then Hotmail, ComputerBits, and Webhost would be weighted at around 0. So we can see that Hotmail and ComputerBits aren't actually quite 0. Webhost is at 0, but it's still giving a predominant amount of the weighting to the FlirtLife dataset. So we can see that it was able to identify that most of the passwords in this password set seem to be best matched with FlirtLife. Okay, so that's a pretty straightforward example. Everything came from FlirtLife. What we did to complicate this a bit more is we took the 4 password datasets again, but this time we took different amount of passwords from each dataset. So we took 5,000 from Hotmail, we took 3,000 from FlirtLife, 1,000 from Webhost, and 500 from ComputerBits. And these all fed into a new password dataset, which have 10,000 users' passwords in it. So again, we plotted what the estimated weightings were for each one of these data sets when it's trying to guess this new password set. So again, the y-axis shows us the estimated Q values. So that's the estimated weightings. And the black lines show us the true weightings. So we can see at 0.05 or 0.55, that's where the Hotmail should be. 0.3 is FlirtLife. 0.1 is Webhost, and then down at 0.05 is ComputerBits. And we can see after one guess made, it doesn't really have that great of an idea. But we can definitely say that within 10 guesses, it has a pretty good idea of how the weightings are arranged. So it has, Hotmail is around the 0.55 mark, FlirtLife definitely around 0.3, and then ComputerBits, it has slightly below the Webhost ones, which is what we expect. So even though these passwords came from different data sets, it was able to identify what the correct weightings were. And so we also showed that this will improve guessing success. So what I've plotted next is just the average number of successes. So the black line is the optimal number of successes. So that's if I guess every single password in the exact right order. This is the number of users I'll be able to compromise. And below that, we have our Q method. So this is using the weightings in order to make effective guesses by choosing from all 4 dictionaries according to the weightings. We can see that if we just choose from what we consider to be the best dictionary, that does slightly worse. That's the dashed line. And then choosing randomly is below that again, and that's the dotted line. Okay, so the next thing I'm going to look at is the nationality. So we already had a computerbits.ie password set, and this is made up of Irish users, and there's 1,795 Irish users' passwords in this password set. But we didn't have a second Irish users' password set. So what we did is we took the a collection from collection number 1, and we took out all the users' passwords where the users' emails ended in .ie, because .ie is the country level domain for Ireland, and we were able to get 90,000 users out that had .ie as their email in their email address. So we chose this as a dictionary, which is made up of Irish users, and then we also took the Hotmail and the Flirt Life dictionaries. And what we want to show is that if we guess the computer bits password set using these 3 different dictionaries, then it should tell us that the Irish users' passwords are doing the best job. So the green line is the Irish new combo semi-private EU combo dist, which is that set of Irish users' passwords, which whose users have email addresses that end in .ie. And then below that, we see that the Flirt Life has been given no weighting and Hotmail has been given some weighting, but it's definitely best to use the Irish dictionary. One interesting thing about this is that Hotmail and Flirt Life, Hotmail was thought to be leaked from phishing aimed at the Latina community, and Flirt Life is predominantly German and Turkish users. So what we could be seeing here is just a language difference. It is still interesting because it was able to differentiate, but what we did next is we included the Flirt Life dataset because, the RockU dataset, because most users in the RockU dataset were English speaking, and so are most Irish users. So we saw the RockU dataset was assigned much more weighting than Hotmail or Flirt Life, but it still concluded that the most weighting should be assigned to Irish users. So we could fairly conclusively say that we probably think the users in computer bits are Irish. We also showed that this did improve guessing, and we also did it as well for German users by taking out the .de domains and using that to guess the Flirt Life dataset, and we got similar results. So the last thing I want to talk about is improving password guessing. So for this, what we did is we wanted to guess the RockU password set, and we wanted to check that it was better to use the multi-arm bandit model than using just individual password sets. So we guessed it using computer bits, Hotmail, Flirt Life, and Webhost. And you can see the purple line is our Q method, which takes the weightings from all 4 dictionaries and then guesses using the best one. So we're still getting the same input guesses basically, but we're just ordering them in a way that is effective. And it's interesting because the Webhost is really bad and Flirt Life is really quite good, and yet the combination of the 4 is still the most effective. Okay, so what have we shown? We've shown that there's definitely a guessing improvement. There was one situation where we didn't get a guessing improvement. That was when we guessed the Yahoo data and we found that the RockU dataset did the best, not the multi-arm model. But in most cases, we found that the multi-arm bandit model did do the best. There is one interesting thing to note, which is that we optimized our multi-arm bandit model in order to get out the correct proportions, whereas if you were giving rewards based on getting the most successes, you'd actually probably get even better results again for the multi-arm bandit model, whereas we were giving rewards for matching proportions best. The second impact is it definitely provides further evidence for the importance of guiding users away from passwords which reflect characteristics associated with demographic or website-specific terms. And because we can automate the recognition of the patterns, we think this could be used to inform password strength meters and block lists. Thank you.